Hello, everyone. My name is Erica Ugbo.
I'm Jenna Sharon.
I'm Joy Harris.
I'm Logan Young.
I'm Steven Nurkowski.
I'm Taruneshwar Ramu. We are going to look about what is systems engineering in our presentation. Let's start off. This is perhaps the most important question of this presentation, but to answer this, we need to first understand what a system is. So let's dive into it. Before we get into the question, what is systems engineering? Let's understand the fundamental concept. What exactly is a system? Think of a system as a set of interconnected parts working together for a common purpose or goal. It's like different musicians in a band, each playing their part to create a symphony. Consider a simple system like a bicycle. It has a handful of components, all contributing to propel the bike forward. There are also intricate systems such as cars, bustling with countless parts, all coordinating to drive us from point A to point B. And then we can take universe as an example. The universe is a big puzzle made of many parts that fit together. Think of the solar system where planets move around the sun or our own bodies. Our body is a great example of system of systems or commonly called as SOS. This means it's made of smaller systems that work together. For example, our hearts, lungs, and stomach each have a job, but together they keep us alive. We won't go deep into SOS today, but just know that it's everywhere. Even in things like computers that use parts and programs to work, all around us, there are many parts working together in harmony, creating a symphony of systems in the world. With this understanding of systems, let's explore a special field dedicated to making these systems work efficiently. That is systems engineering. All right, now coming back to the topic of the day. What is systems engineering? Imagine you're piecing together a complex puzzle. Now think of each puzzle as elements of a school: classrooms, teachers, students, and timetables. Systems engineering ensures each of these pieces fits seamlessly, painting the complete picture of a well organized school. It's the art and science behind creating and managing such integrated systems. So, when and where do we apply systems engineering? It's applied every time there's a complex system to design or manage. Picture setting up a school. From the timetable that structures your day, the allocation of classrooms, to the roles of teachers and the flow of students during the breaks, the systems engineering is an action there. But it's not just schools. This discipline stretches to constructing bridges, sending satellites to space, and keeping hospitals running smoothly. From the school bell ringing on time, buses arriving and departing, to ensuring your favorite school event happens without a hitch, that's the magic of systems engineering. Now, why do we need systems engineering? Think of a school day without a set timetable or a lunch break that clashes with classes. Chaotic, isn't it? Systems engineering brings order to such scenarios. It's like having a meticulous school principal ensuring everything is organized for the best student experience. Who are systems engineers? They are the planners, the strategists, the behind the scenes orchestrators. In the realm of a school analogy, systems engineers are like the school principals and administrators. They chart out the school day, decide which teacher teaches what and when, and ensure resources like textbooks and labs are optimally used. They are the reason your school day flows smoothly, with each part fitting perfectly into the larger picture. By the end, you will appreciate that just as school thrives with meticulous planning and organization, our world benefits from the careful design and management that system engineering provides. And now I'll pass off to Joy.
Hi, I'll be discussing life cycle stages. Every system goes through 6 stages in its life cycle. These stages are concept, development, production, utilization, support, and retirement. The systems engineer is responsible for defining what these stages will look like for the system. The concept stage is where the problem that the system is trying to solve is defined. Systems engineers will work with the stakeholders to define what they want to get from the system. Stakeholders are all the groups of people that will interact with the system. This can include the users, trainers, and maintainers, and more. Once the stakeholder needs are defined, the systems engineer explores possible solutions. During the development stage, the systems engineer turns the stakeholder needs into system requirements by adding information about the system performance that is needed to meet these stakeholder requirements. Once the requirements are decided on, the system is developed, verified, and validated. The production stage is where the hardware and software needed for the system is developed and tested, and any equipment needed to manufacture the system is created. Once the tools and equipment are completed, the systems engineer works with manufacturing teams to make the system. The utilization stage is where the system is transferred into the user's hands and is operated. The support stage happens at the same time as the utilization stage, and as the name suggests, provides support for the system's operation. This includes troubleshooting issues and making repairs when needed. The retirement stage is the end of the road for the program and is where the system is removed from operation. All 6 of these stages can have a lot of overlap, and more than one can be happening at a time. And depending on the program, these stages can be done more than once as the system's requirements change over time. A good example that can be used to understand how the life cycle stages work is a bridge. People start with needing to cross a body of water. This is a stakeholder need. In development, the system engineers need to define requirements like the bridge length, height, design, and strength. Then in production, the bridge is built by the construction crews. The systems engineers work with the construction crews to make sure that the bridge stays on schedule. Once the construction is completed, the bridge is open for people to use, which starts the utilization stage. When people are using the bridge, so the support stage starts because it is important to make sure it doesn't fail by doing maintenance. Once people decide to retire the bridge, it is demolished, or the systems engineer can decide to add on to the bridge, restarting its life cycle. I'll pass it off to Stephen to talk about mission analysis.
Thanks, Joy. In systems engineering, a mission analysis is like coming up with a big plan for an important event or project. While conducting a mission analysis, it is important to ask yourself these questions. What is the goal you are looking to achieve? What needs to be done? How can it be done? And who should be involved? For example, let's say you're on the committee to plan for the next field day at school. The mission analysis would be done when the group of students and teachers sit down to plan which day works best, what activities should be included, what equipment or materials is needed to do those activities, which teacher should be involved and in charge of each of these activities, and what the goal is, which obviously is to plan for the most fun field day possible. Like I just mentioned, it is important to figure out who is involved and who is interested in your project or event. In systems engineering, we call the people who are involved or interested stakeholders because they have a stake or interest in how things go. Going back to the field day example, who would be the stakeholders involved? Well, we know that the students and teachers involved in the planning are stakeholders. Also, the school faculty, staff, or parents that are volunteering who might be supervising or running events, even if they may not have been a part of the initial planning, are stakeholders too. And finally, all the students who participate in field day are considered stakeholders. Since the goal of the field day is for the students to participate and have fun, you are considered the primary stakeholder. So you can think about a stakeholder as anyone who has an interest in the project or event, but for different reasons. Now I'm going to hand it off to Jenna to talk about system requirements.
Thank you, Stephen. So system requirements, they describe the capabilities that the system must have in order to satisfy the needs of those stakeholders we talked about. They translate the stakeholders' needs into the technical needs of the system, and then the development team can use that to build and test their design. All requirements follow a standard shall statement shown on the slide, where it describes what the system shall do. There's some variations on this depending on the requirement and if there's other clarifying information needed, but every requirement will follow that general format. There are a couple of different types of requirements that serve different purposes. You can have functional requirements, which describe the required functionality of the system. You can have performance requirements, which define how well the system needs to do those functions. And you can also have non-functional requirements that deal with the operational conditions of the system, like how the environment interacts with the system or how well the system can be maintained. Together, the full set of requirements provides a full list of criteria that the system needs to be tested against to prove that it was designed and built correctly. When writing functional requirements, you want to figure out what the functions of the system must perform. You need to figure out what its intended purpose is. So to do this, you want to ask questions like, what does the system need to accomplish? How will the system be used? How will the system be supported during its life cycle? Now let's go back to that bridge example we were talking about earlier. How is that bridge going to be used? Well, maybe it will be used to allow cars to travel across it. What does our system need to do to accomplish this? So for this, our functional requirement would be the bridge shall allow cars to travel from point A to point B. Now looking at performance requirements, we want to think about how well does the system need to perform. Back to our bridge example, how many cars does our bridge need to be able to support? Well, cars have a lot of weight, so that's important for our system to know about. So let's say that the maximum car load that we expect our bridge to need to support is 200,000 pounds. Well, we'll need a requirement that says the bridge shall support a load of at least 200,000 pounds. Now, non-functional requirements deal with the operational conditions of the system. This can include the manner of the system's operations, such as how safely the system operates or how reliably the system operates. It also includes constraints on the system, such as environmental restrictions. So again, back to our bridge example, let's say our bridge is being built over water, and we have a stakeholder need to not adversely impact the marine wildlife. Well, then we'll need a non-functional requirement to define the constraint of the system. For example, we might have a requirement that says the bridge shall impact water flow of less than 0.5%. Now moving on to the architecture, it takes the needs of the stakeholders, those requirements we've already defined, and the uses of the system, and translates all of that into a design that our design team can then implement. The system architecture, you can think of it similarly to how an architect designs the blueprint for a building based on the needs of the building. A system architect first spends some time analyzing the uses of the system, any constraints on the system design, and the stakeholder needs and concerns. They take all this information and develop several viable candidate architectures to consider for the system. Then they consider these viable candidates and select an architecture to move forward with. That architecture is documented and maintained by the architecture team so that the development team can develop the system following that selected architecture. Looking back at our example of the bridge, we know from our stakeholder needs and system requirements that our bridge needs to cross a body of water and transport cars across it. There's several different bridges that architectures can consider for this design. We could use an arch bridge, shown on the left. However, these bridges are typically only for pedestrian traffic because they need to be very large to carry those heavy weights. We could also use a suspension bridge, shown in the middle, since that suspension bridges allow for the largest bridge expanses and are very flexible. And then on the right, we could use this cable-stayed bridge. These ones are similar to suspension bridges, but are less flexible and cheaper to build. So an architecture team would consider these design constraints and use cases of the bridge we're developing and narrow down these several architectural solutions, and then select the proposed solution and move forward with. Now I'll pass it off to Erica to talk about verification.
Thanks, Jenna. Verification and validation are types of technical processes that work to make sure the system elements were built right. Though they sound very similar and both work towards the same cause, there's a key difference to notice between the two. The purpose of verification is to prove the system does what it was intended to do, whereas the purpose of validation is to prove that the system is beneficial in its intended use. As mentioned in a previous example, our stakeholder functional requirement would be the bridge will allow us to travel from point A to point B, because essentially the customer wants to get from point A to point B more efficiently. It makes sense that our system would want to have some form of transport embedded into it. That being said, the design of the system would be a bridge design, like we just saw. And to begin implementing this process, we need to start doing things like buy bridge materials and find employees to help build this bridge. Constructing the bridge is what actually integrates the structure into our system, that sort of manual work. So now that we have our bridge ready to go, let's test it using those verification and validation technical processes. Did I build it right? Does this bridge meet the original system requirement and design? We can answer yes if the bridge is secure between points A and B and meet the rest of those system requirements. Now we ask ourselves, is the bridge helping the way it's supposed to, and how can we tell? To validate the bridge is working efficiently in the way we intended it to, the user must be able to safely get across the bridge quicker than before the bridge was made. Using quality assurance methods give us, the system engineers, more confidence in meeting stakeholder requirements. The goal here is for products to conform to stakeholder requirements, meaning that they can achieve what the customer asked us for without having any defects or flaws in the product. In order to do this, engineers use a variety of methods to break down any nonconformances, like by using a checklist. Engineers also use methods to backtrack and see what went wrong if anything bad happens to the product. A 5 why is a common problem-solving technique. It basically forces you to continue asking yourself why something happened until you can get to a solvable root cause of the problem. And sometimes you might even have more than one root cause to a problem. In situations like that, fishbone diagrams visually show what might have caused the problem and categorize them under different factors. These contributing factors can be things like the environment, the written procedure, or simply human error. Quality management, on the other hand, helps a company manage the quality of their product. In order to do this, engineers use methods that give details on certain data characteristics of the product, like, for example, how long it takes to make each product or the size of parts in the product. Statistical process control, or SPC for short, does this by plotting where each part falls for whatever characteristic you're measuring. So if all your dots fall within your limits, that means the method you're using to make the product is pretty good. If the dots look a little wonky and are all over the place, we may need to step back and think of better ways to maintain consistent quality in the product. Having good quality products is really important. Quality helps system engineers understand processes and optimize performances. It also lets us make good decisions and find ways to improve based off data and maintain good relationships with customers while addressing risks in our processes. On that note, I'll pass it off to Logan.
Thanks, Erica. So any project you do has some amount of risk involved. Risk that something could break, risk that something might not work, or even risk that something might cost too much money or time. The way that we deal with these risks is through risk management, which essentially means what part of the system is risky and what can we do to decrease that risk. To try and find out what part of a system is risky, we should ask what will happen if something goes wrong and how likely is that to happen. If we can answer these questions, then we get a good idea of how much risk there is. We use this table in the bottom right to compare how likely and what the consequences will be when it comes to risk. If the combination of the likelihood and the consequences falls in the red section of the grid, then that's bad and needs to be fixed. If it falls in the yellow, that's not as bad, but it could be better. And if it's in the green, that's probably fine. This gives us a good idea of how to categorize risk. A good example of how this could be used would be our example of the bridge. There's a low likelihood that a boat going under the bridge will collide with one of the pillars. This is unlikely, but if it were to happen, there could be significant consequences. What we can do to decrease this risk is add a small barrier around the pillar that will decrease the consequences if it gets hit. We can see in the grid that this example doesn't change the likelihood of it being hit, but will decrease the consequences. This is one of multiple ways to decrease risk. We can look to avoid risk by preventing problems from happening in the first place. We can look to control it like we did in the example, or we can try and transfer it to something else. Like if we were to put a protection in place, then the risk would no longer be the thing itself failing, but the protection failing. Now, we have been using this example of a bridge for a little while now. Let's talk about some real examples of system engineering design. The bridge that we have been talking about is real and called the Øresund Bridge, and it's in Europe. The Øresund connection links two major cities, Copenhagen, Denmark, and Malmö, Sweden, by using a combination of a tunnel, an artificial island, and a cable-stayed bridge. The bridge of the Øresund connection became the longest rail and road bridge in Europe. The massive overpass was built over the span of almost 5 years, and in design and planning phase until 1999, it stretches nearly 10 miles. The construction of the Øresund Bridge not only resulted in a historic milestone for both countries, but as an inventive and systematically engineered art. The combined efforts put together by several countries was arguably one of the greatest systems engineering efforts by Denmark and Sweden set forth during this era. This is just one of the countless examples of world-changing projects that were made possible by systems engineering. Other examples are putting the first man on the moon, or even the International Space Station that is still in orbit today. If you are interested in high-tech projects like these, pursuing a career in STEM can give you the skills to work on the next world-changing project. So, in conclusion, thank you for listening to us, and I hope you learned something about systems engineering.